Hello, everyone. My name is Fan, and I'm a fourth-year PhD student at Georgia Tech, advised by Professor Taesoo Kim. So today I will be presenting our work, PRIDWEN. Originally, it's the name of the shield of King Arthur, and which here represents a framework for universally hardening SGX program via low-time synthesis. This project is a collaboration between our lab and Intel. In today's world, cloud computing is everywhere, led by well-known names such as Amazon Web Service, Microsoft Azure, and Google Cloud Platform. Cloud computing has been a major enabler for applications across different services and devices. To make use of cloud platforms, user data is transmitted to, used by, and stored in the cloud. However, as a cloud provider has the total authority of the cloud infrastructure, while not necessarily could be trusted, data security has been one of the major concerns with cloud. Being privileged, a malicious cloud provider can easily compromise the security of data in transit, data in use, and data at rest. Thanks to the advance of security research, we have corresponding strategies to protect the user data at each stage. To protect the data in transit, TLS and SSL are applied over the network. To protect the data at rest, the cloud provider offers disk encryption in order to ensure integrity and confidentiality. And to protect the data in use, here comes our main character today. Intel Software Guard extension, shortened as SGX, is developed and deployed to provide a trusted execution environment so that the user can be confident that even when the cloud provider becomes rogue, no secret could be stolen when the user workload is being executed on the cloud server. So how is SGX able to provide such a trust? Let's briefly get some background. On the server side, during runtime, the CPU is constantly fetching the user code and data from the memory for execution. At the same time, the privileged software, such as operating system and hypervisor, can issue external memory accesses in order to peek into the execution context. If the privileged software is malicious, everything during execution is exposed. SGX provides a protected execution container called enclave, which consists of an isolated memory region enforced by the CPU hardware. First of all, only the enclave is allowed to access the isolated memory region, so accesses from elsewhere, even from the OS and the hypervisor, will be denied. Second, memory encryption by hardware key fused on the CPU during manufacturing is enforced on the isolated region. The memory content will only be decrypted when entering the CPU for execution and re-encrypted once left the CPU. Physical attacks such as memory snooping therefore cannot exfiltrate any useful data. Lastly, SGX provides the capability of remote attestation, by which a user can attest that the code and data are deployed into genuine SGX enclave with the most updated security features. However, life is always not easy. The Achilles heel of SGX lies in a category of attacks called side channel attacks. Inevitably, when it comes lower into the execution stack, SGX programs share stateful hardware resources, such as cache and page table with other processes. The shared resources create unintended information channels, which we call side channels. Although with the security guarantees of SGX, privileged software cannot directly access the secret inside an enclave. Through side channels, the attackers are able to exfiltrate secret data indirectly. So cloud providers with total authority over the servers have natural advantage as side channel attackers to conduct secret inference with low noise and high resolution. SGX side channel attacks have been well researched in academia, with published research papers in various top conferences. Common shared hardware resources for launching SGX side channel attacks include page table, cache, branch predictor, translation look-aside buffer, and CPU execution pipelines. All those attacks allow the attacker to infer fine-grained information inside the enclave. As a result, the security guarantees of SGX are compromised as long as those side channels are present. So how are the SGX side channel attacks addressed? Against those attacks are various mitigation schemes from the academia and industry, each targeting different types of side channel attacks, or just serving as a general hardening technique for SGX. They all share similar design choices. First, they require no hardware modification for quick rollout. Second, they are enabled by code instrumentation via compiler and require minimum manual effort for best usability. During compile time, customized compilers will automatically transform programs into hardened ones by inserting extra logic. Let's take a look at how one single instrumentation-based mitigation scheme gets deployed on SGX applications. Using a customized compiler designed for a specific mitigation scheme, the user source code is locally compiled into a protected binary. The hardened binary is then securely transmitted to the remote and executed inside an SGX enclave on an SGX-capable machine. However, each scheme, as we saw before, targets limited types of attacks. While the problem is that multiple side channels can coexist. Therefore, to defeat multiple side channel attacks at the same time, we need to compose multiple mitigation schemes together. Now, instead of targeting one type of side channel attacks, for example, hyperthread-based attacks, we need to apply schemes targeting other types of side channels at the same time, such as cache attacks and page fault attacks. When we want to deploy multiple mitigation schemes, if follow the current strategy we saw before, some sort of mega compiler will locally compile the user code with multiple mitigation schemes together. And the hardened binary will be similarly transmitted to the SGX enclave on the target machine for execution. But is that really the true story? Unfortunately, natively composing multiple mitigation schemes locally creates several problems for distinct remote platforms. For example, if the remote server already has hyperthread disabled, the scheme targeting hyperthread-based attacks will be redundant and incurs unnecessary performance overhead. Meanwhile, if there's no Intel TSX hardware support on the remote server, the binary hardened with TSGX, a scheme against page fault attacks, will simply fault on TSX instructions, making the application undeployable. Not to mention that mitigation schemes might be incompatible with each other by design or implementation due to the unawareness of each other during development. They all happen because of the static approach of enforcing schemes at local compilation time. So when can we make the best decision of the mitigation schemes to be applied? We believe that the decision should be delayed as close to the final execution as possible to best fit the target SGX platform, as well as the coexisting mitigation techniques. How it will look like are as follows. Instead of applying mitigation schemes locally, we will select and apply mitigation schemes on the remote side after the binary is deployed to best fit the capability of the runtime platform. For example, the target platform has no TSX support with hyperthread disabled. Then corresponding schemes, the highlight here, should be omitted to achieve best performance and compatibility with the platform. To achieve such a strategy, there are several requirements. First, we should be able to detect the hardware configuration of the target platform, such as whether TSX is available or hyperthread in this example. Second, we should selectively enforce schemes to achieve the best performance and security for the specific platform while avoiding conflicts and errors based on the configuration we have. Finally, we should be able to validate that the scheme are enforced faithfully to provide the expected security guarantee. So PRIDWEN is our answer to this. Let's take a look at an overview of PRIDWEN and see how it satisfied the requirements. So from a bigger picture, PRIDWEN is a binary loader inside the SGX enclave. First, PRIDWEN's prober identifies the hardware and system configurations of the target platform in a trusted way. To selectively enforce schemes, PRIDWEN's path manager first determines an optimal set of feasible instrumentation passes based on the identified hardware configurations. Then, PRIDWEN synthesizer accepts the user-provided binary and hardens the program with the chosen instrumentation passes before loading it into the target SGX enclave. Finally, to allow validation of enforcement, PRIDWEN's validator verifies whether the final executable is hardened as expected and provides a functionality for developers to remotely verify both the process of synthesis and the hardened binary before execution. However, meeting those requirements under SGX is non-trivial. For example, instructions that we normally use to query the hardware capability of the system, such as CPU ID and syscalls, are not allowed in SGX enclave. Besides, under the threat model of SGX, operating system is not trusted. A malicious operating system can simply return false information about the hardware configuration. For example, lack of TSX when TSX is actually available, to bypass enforcement of certain mitigation schemes. So, how to detect hardware configurations in a trusted way in the presence of privileged attackers. Meanwhile, the target binary is dynamically generated by the PRIDWEN synthesizer inside the SGX enclave, while SGX remote attestation only supports attesting static contents in enclave upon enclave initialization. So how to sustain the chain of trust of SGX remote attestation, even in presence of the dynamic code and data. Challenges exist for selective enforcement of schemes as well. Due to time constraint, this presentation will focus mainly on selective enforcement of schemes. For more details, please refer to our paper. So we call PRIDWEN's approach load time synthesis, by which the binary is synthesized and when it's being loaded for execution in the enclave. PRIDWEN on the remote side takes the intermediate representation, or IR, of a user program as input. It supports compilation and instrumentation of the IR to apply different instrumentation-based mitigation techniques. PRIDWEN also provides various APIs at different granularity levels for implementing mitigation schemes as instrumentation passes. We decided to use IR instead of native binary as input for several reasons. First, IR is friendly for code analysis and instrumentations and has been used for such purposes thanks to the advance of modern compilers. Second, IR is an abstraction of the source code and is platform independent, so the program in the form of IR is not restricted to a particular platform like native binaries. For PRIDWEN, we choose WebAssembly as our target IR. WebAssembly is a lightweight IR with a small instruction set, which only adds a small footprint to the enclave's trusted computing base. WebAssembly is a target IR for multiple high-level languages such as C, C++, and Rust, so that the choice of development language for the user is more flexible. And finally, the compilation of WebAssembly is very straightforward, providing flexible instrumentation options. As we can see here, the PRIDWEN backend is only 1.26 megabytes, comparing to the LLVM x86 backend, which is about 3 magnitudes bigger. So in order to convert this simple C program into a WebAssembly IR, the user will first compile the C program into a WebAssembly binary. The compilation is carried out by open-source WebAssembly compilers, such as mscripton, and the process requires no source code change. Upon receiving the WebAssembly binary, PRIDWEN will decode it into readable WebAssembly IR for instrumentation and compilation into native code. The WebAssembly single-pass compilation allows us to enable flexible instrumentation for mitigation schemes at both IR and native level. For example, for a single instruction in WebAssembly IR, we are able to hook either before or after the stack operations and insert extra logic. Meanwhile, for conditional statements in the WebAssembly IR, we can hook before or after the corresponding native code. In order to hijack the control flow or insert memory fence instructions for mitigations against speculative execution, for example. To facilitate easy adoption of PRIDWEN for developers, we provide convenient instrumentation APIs at different granularities. At WebAssembly IR level, developers can instrument at function level at each control statement or at a single instruction. At native level, developers can instrument at each machine instruction. With such a capability, PRIDWEN can conveniently support most, if not all, instrumentation-based mitigation techniques against SGX side channel attacks. So after we know how PRIDWEN works, let's look at an example to see what PRIDWEN looks like in action. The PRIDWEN loader here detects that the target platform has TSX available and hyperthread disabled, for example. The path manager gets the configuration information and decides to apply TSGX and ASLR as the optimal set of mitigations to benefit the performance of TSX hardware and prevent the redundant protection of hyperthread-based attacks. On another target platform, the PRIDWEN prober detects that TSX is not available, while hyperthread is enabled. Based on the probed configuration information, the path manager decided to enforce ASLR co-location tests for hyperthread-based attacks and varies as a sole alternative to TSGX when TSX is not available. To show the runtime overhead of the PRIDWEN loader itself, we measure the execution time that PRIDWEN takes to synthesize native binaries with different compositions of mitigation schemes. We divide the execution of PRIDWEN loader into 3 stages: the initialization stage, the synthesis stage, and additional overhead when the ASLR is enforced. Overall, the overhead of synthesizing native binary from a small program is around 50 to 60 milliseconds, while from larger programs it's less than 500 milliseconds. This overhead is only imposed once, when synthesized the program for the first time. We evaluate the runtime performance of PRIDWEN synthesized programs using realistic applications such as Lite, SQLite, and libjpeg. First, without applying any mitigation schemes, we measure the relative runtime performance and compare it with the native versions. This metric tells us about the overhead of using WebAssembly as an IR for compilation. The evaluation results show that PRIDWEN slows down Lite by 1.5 times, SQLite by 1.3 times, and libjpeg by 1.4 times. Meanwhile, recent study shows that spec benchmark compiled using in-browser WebAssembly just-in-time compilation slows down by 1.45 to 1.55 times, which is comparable to what we have observed. When mitigation schemes are enforced, in the case of libjpeg and SQLite, the performance slows down by 1.9 times on average when only hardware-based schemes are enforced, and 3.4 times when software-only schemes are enforced, which are both comparable to the original implementations of those schemes. To conclude, we first talked about that SGX side channel attacks can coexist, while each mitigation scheme targets limited types of attacks. We then pointed out that the existing model for deploying mitigation schemes is limited under such an attack scenario. We proposed PRIDWEN to address the challenges of scheme composition. PRIDWEN detects the hardware configuration of the target platform in a trusted way and adaptively enforces mitigation schemes with an enclave loader. And PRIDWEN is extensible to support more instrumentation-based mitigation schemes. PRIDWEN is open source for the community to test, use, and contribute. With this, I conclude my speech, and I'm happy to take any further questions.